y'all, and welcome to the most electrifying podcast on social media. I'm your host, Willie Snyder with NEC Code, coming to you live from the Mile High City in Denver, Colorado. I'm joined by my awesome co-host, Mr. King James Stallcup of the Stallcup Electrical Education, the best online electrical education you could get, period. And we dare you to show us something better. We haven't seen anybody do it yet, sir, but
They're not going to.
Yeah. I really appreciate everyone joining us every week. It's so much fun. We have an easy Willie Quiz for James tonight. He's been nailing them, knocking them down 3 for 3. So now tonight's a little chance for me to see if he's got some good guesses in him for the Willie Quiz tonight. And I really appreciate everyone, all the participation I had in Nat King Code. This myth that I ran this week was based on a real thing that I ran into out in the field. And James was kind of slacking on one of his illustrations, so he had to get finished up with that illustration. So I kind of boosted him up, get his illustration going for tonight's myth. And I really appreciate everyone, like all the participation and comments. And I hope everyone gets a chance to join up tonight and kind of see what we're talking about with the myth, and just having so much fun, just enjoying the electrical trade and enjoying all this stuff, like the code making process and everything, So it's a lot of fun. I appreciate you, James, for putting these together.
Oh, yeah. Yeah, it's all part of the master plan. At least that's what they tell us. We submit some proposals and stuff, and apparently we're part of some master plan to take down the code making mantles. Anybody else can submit them, but we submit them. It's a master plan. I think they're just trying to start something to get things going. You had a post I thought was hilarious. Jeremy showed me where you showed me a screenshot and you showed it. Now they're all quiet and trying to defend him and all of this stuff. I mean, it just goes to show the hypocrisy. They don't really care what anybody else thinks.
Awesome, Mike Barr.
Hey, Mike,
awesome.
How you doing, brother?
Thanks for joining us tonight, Mike. Appreciate you.
Yeah, old Dad, he's got him a cold in there. He's trying to get feeling better. He sort of caught it a little bit from me after last week. Thursday, Thursday I wasn't feeling too good anyway, but Friday it started hitting me, and I coughed Friday and Saturday. Then pretty much Sunday is over, but he got it Sunday, started getting it, and he's sort of been down under the weather for. I mean, this is his 4th day, so I guess being in your 80s, you don't recover like us young bucks.
True.
So
yeah,
anyway, I've been taking food to him, feeding him, and everything. So.
Yeah, it's awesome to have guys like Mike Barr, great individuals in our audience. Really appreciate joining Mike. And, it's so much fun for me to do these because they're pretty simple to put together. And, I make like these, I don't know if Mike's joined in the last few weeks, but I make these like really easy quizzes for James, and try to get him to have his like he's always right on his second answer. So as long as he gets his second answer right, then we can give him 100%. So, but it's a lot of fun doing these. I appreciate everyone that joins up and has subscribed to the channel. Like we're doing really good, and there's a chance. I'm not sure. It's too early to confirm, but we might have our first Journeyman of 2024 that is a member of Nat King Code and a member of our group. So that's actually going to be a licensed journeyman, Colorado's first, newest journeyman. I'm crossing my fingers, so I'm crossing my fingers for you, Chris. So
Chris, all right.
I appreciate Chris joining for our exam prep class that we've done every week, and hopefully it helped you get that J-Dub license today, so we'll
Amen.
see. I haven't heard if he passed or failed yet, so knocking on fake wood.
Hopefully he did and comes on here and lets us know. I was
Yeah.
looking. Yeah, we're at 247 on the YouTube channel, so it's growing.
Nice.
So,
We're a quarter of
not
the way
bad.
there, so make
Yep.
sure you get your grandma and your uncle and your cousin and even your kids to subscribe to the channel, and we'll keep bringing good content every week. So we really appreciate it. We do this for fun. It's a lot of fun for us, and like I say, I can't remember what I did for the meme this week, but I think it was pretty funny.
All right, let's roll it. See what you did.
So yeah, that's kind of a funny one because a lot of guys, I'm kind of guilty of that at times. You know, when you're just like, you know what, I need to get an answer on this. Why don't you just go over here and do this, and I'll get back with you when I get some answers or something.
Never
you know,
show the apprentice you don't know.
Exactly. But
That's
that was a
funny. I
pretty
like that
funny
one.
meme. Yeah.
That's a good one.
Yeah, I just ran across it, but like I say, it's pretty cool when we run a meme group, and so we from time to time come across memes, and we have like the high voltage electrical memes, and all these different groups. The electrical code discussion for awesome electricians. We're over 17,000 now members. It's just so awesome. It's growing so fast, and I'm over 1,700 followers now on NAC Code, which is awesome. And I built NAC Code as a free page just to help people learn the National Electric Code. And I'm always constantly getting ripped down, and guys is saying that I can't read and all this stuff. And all I'm trying to do is just bring an element that kind of gives people a way to kind of learn and study the code. So it's gonna be awesome. Like I say, I know I was probably wrong on like my code reference for the myth of the week. I think I quoted something that was probably not on the right path, but I'm glad that's why I brought James along this week, so that he could kind of set us straight on the myth of the week, and just let everyone know I am making these into a Spotify podcast called the Nat King Code Podcast, so you can find it on Spotify, and you can join us audio and listen to the audio, and you don't have to tune into every show. So,
All right, let's roll the myth and talk about it.
It's time for Myth of the Week.
Alright, so this is based on an actual true thing that happened. One of the job sites I was on, and they thought that all they had to do was just hit that point where the water enters the building. You could see that on the left, and per the code reference, the water, the main water entry needs to be hit within 5 foot from where it enters the building. And then you can see there that they took the electrode conductor across and jumpered that meter and backflow preventer. And so that's kind of basically what this myth is based off of. I know it was a little tricky for me to get the wording right, and it's probably it's close. It's probably not 100% accurate, but I was just trying to get my point across that the myth is that you don't have to jumper that all you have to do is just hit that water entry area location. And so that was the whole thing. What I was trying to drive with this myth this week, and there's a lot of guys out there that like, well, the code doesn't say you have to jumper that, you know. But I know James is gonna do a good job tonight, going and setting me straight for one, making sure I understand which code reference is requiring us to jumper that. You know, I know in your case, James, you have like maybe a water softener, but anytime
Yeah,
you have like water softener, meter, backflow preventer, any of those are non-conductive pieces, and you have to jumper them so that you maintain that continuity of that metal water piping throughout the structure.
correct. When you go over and look at your grounding electrodes, you're going to look over at 250.52A1 in this case for the metal water pipe. And basically,
Right.
it's going to tie the inch so you can use the grounding electrode, blah, blah, blah. And that has to be connected. You get in your installations over and 250.68C1, and that's where it's going to tell you you're connecting within 5 foot and all that stuff. Okay.
Right.
Now, when you get over here, what this we were getting into, we're still in 68. This is the installation, but you're going to be looking at B, making sure you're providing that effective grounding path. Matter of fact, we even show one if I went outside and I was tying into another electrode and somebody come out and it was in conduit, you would have to bond that conduit with that grounding electrode conductor. Okay, and
Sure.
we show that in another illustration. Matter of fact, I just finished it the other night. I've been going through updating those illustrations, but what it says here, the connection of a grounding electrode conductor or bonding jumper to a grounding electrode shall be made in a manner that will ensure an effective grounding path. Where necessary to ensure the grounding path for a metal piping system used as a grounding electrode, bonding shall be provided around what? Insulated joints and around any equipment likely to be disconnected for repairs or replacement. Okay?
Nice.
So when you get over here and you look at this is a good illustration, we show different areas where you get in where, like the one on the left, we're showing a filtering device there and making sure that you keep the continuity and everything. Here and by the panel where it's coming in, we put a softening device in there, and we're basically just pointing out that when you're going to provide this bonding and everything, you need to do this in around the metal water pipe to provide that effective grounding path back. Okay, so it's basically making sure everything is what? Bonded. And you don't have something that's put in between it that will take and affect that effective path. And that's what it's doing right here. So when you go in and you look at all this stuff, that helps take care of it.
Yeah, and what I like about that, go back to that illustration really quick. A lot of there's a lot of confusion around, and this might be another myth that I run, is it says that equipment, that grounding electrode conductor needs to be continuous. Well, you're showing it in that picture as continuous. It's electrically continuous.
Mm-hmm.
So it doesn't mean the wire has to just be one piece. Like, a lot of people get confused on that, and so I really like that how you did that in your illustration, because that is considered electrically continuous,
Sure.
even though it's not one piece of wire. So I just wanted to add that in there because that's a good illustration in there. I like how you did that to where it's required to be electrically continuous, not mechanically continuous.
That's right. And that's when we take a lot of time developing those. I actually did that on the 17 because we're doing everything in the 17. We're bringing all the illustrations from 17, 20, and 23 are all going to be updated in color. And that's why one of the sections is wrong in there. But regardless of that, the point was still made. But we're updating all those illustrations right now. And there's going to be a major upgrade. And I will say this, the grounding looks fantastic because we show all the colored wires and everything. And of course, since it's on a white background, I've created like a grade shaped box around the conduit and everything, so you can see the white wire and all that. So there's a couple of things I had to do here and there, but when you go in and look at it, it's like, man, that looks good. So anyway, that's what we're working on. So
awesome.
All right, we ready to get into this topic of the week and get back into our Journeyman Masters?
Let's do it. Get your code books out, fellas. And
here we go.
Ladies and gentlemen.
All right. We're right back into what we were doing last week. We're just continuing on. We're calculating conductor ampacities. Last week we got into talking about doing the taps, and like this one here, we're in 240.21B1. And as I said, and I'll rephrase this one more time, if you're doing a tap that's 10 foot or less, you divide by 10. All other taps you take at a third that are greater than 10 foot, and then if you have a transformer and a tap, you do the secondary to third, or the primary to third, but when you get to the secondary, you're going to take it at a third, but you also need the ratio of the transformer, okay? Sure. So we'll go through this real quick. This shouldn't take long. Everybody should have these taps down pretty well now. But here in the illustration, I've got a 600 amp overcurrent device upstream. I'm going to make a tap off of that feeder circuit that's going out. So I'm going to divide that by 10. That'll give me 60 amps. I go over, look at table 310.16. We're using the 75 degree C terminals. Come down the next size above at 65 amps, which is going to require a number 6 conductor. So therefore, we verified that the 65 amps is greater than the 60 amps. Therefore, the size THW and copper conductors are number 6. Very simple. Then I go to a 25 foot tap. We're in 240.21B2. I said everything else we take at a third. So I take 600 amps at a third. That's going to give me 200 amps. Once again, I go to table 310.16, 75 degree C column. Come down. You're going to pick up the next value equal to that. In this case, it's 200 amps. Come across the left-hand side, it's going to tell you it's a 3-aught conductor. So your size THW and copper conductors for this tap will be 3-aught. All right. Then we're going to go to the next one. This is where we actually have a transformer in the tap. And I said on the secondary, you got to get the ratio of the transformer. And in this case, we have a 408 volt primary and a 208 volt secondary. The upstream overcurrent protection device is a 300 amp. So when I'm doing the primary tap, I'll take the 300 amps at a third. That's going to give me 100 amps. Go to table 310.16. The next size above that, or equal to that, is 100 amps, which is a number 1 aluminum conductor. And this is a trick question here, because what will happen if you're taking the test, you'll look at the conductors we gave in this case, and we're telling you we're using THW and aluminum instead of copper here. Okay? So, and that'll be you got your first column, then you go over the next set, you'll see the 60, 75, 90 degree C over there, and that'll be your aluminum conductors. Okay? Now, when I look at calculating the secondary conductors here, I need the ratio of the transformer. So I'm just going to take the 208 volts divided into the 480 volts. Then I'm going to multiply from that point a third and the 300 amp overcurrent device. That's going to give you 231 amps. The next size up above that is a 350 kc mil aluminum. So as you can see, doesn't matter what you're doing, which conductors you're using here. All you have to remember when you're doing these calculations is if it's 10 foot or less, divide by 10. Everything else, take at a third. And if I have a transformer in the tap, I got to get the ratio of the transformer on the secondary. That's it. Okay?
Yeah, and it's important for guys out there when they're taking that exam to like it's easy, and I know this happened to me, is it's easy to try to just go too fast and not read and just, and I was just as guilty as anybody. You have to remember to think of every little thing when you're doing this, as far as like the aluminum, just kind of like what James was saying. He throws that trick in there because, and I'm guilty of that too. I just think everything's copper, and then
Mm-hmm.
next thing you know, all of a sudden the answer is on there for copper.
Mm-hmm.
So that's what you have to realize when you're taking that exam, is that the wrong answers are on there too, and they seem right because if you do the calculation, it'll come out to an answer that's copper. And so you just have to know that they're intentionally trying to trick you, and you just have to make sure. So that was just something I wanted to add.
Sure, and it is true, and that's why we bring this stuff up. And this one here, this is 100-foot tap, and you'll notice we also put some rules in there, for how that would be installed. 30 foot up above, or panel board and all this other stuff, and then 25 foot maximum. So we put all that stuff there if you want to reference it. But in this
Okay.
case, we got a 400 amp up screen. Take it at what? A third. Everything that's left
Yeah.
at a third. That gives you 133.3. And in this case, we're doing copper. So I'll go to table 310.16, 75 degrees C column. The next size above the 133.3 is 150. Come across, it's going to tell you that the size PHW, and copper conductors are required to be 1 ohm. Simple. And if
Nice.
you notice, I didn't change anything. I stayed the same process all the way through. I took a third for everything that was over 10 foot. The only difference I did was on the secondary of a transformer that's in a tap. I took the ratio of the transformer part of that calculation. Okay? So
Nice.
everybody should be able to understand that pretty easily. It, I always say, a lot of times people overthink things. And when I was teaching people for Journeyman, masters, whatever, I'd always give these little insights like that. Don't overthink it. Just remember these rules, like a rule of thumb. If you follow this, you can go find the information you need, but at least you know how that's supposed to be calculated. Okay?
Sure.
Now, this is where we get in. Now, they actually came in, I forget what cycle it was, but they come in, and a lot of people used to say, oh, just tap the secondary side of that transformer. Well, that didn't make it a tap. Those are actually uh, connections from the secondary of the transformer. Okay, so
Right.
they come in and they relayed this article out, specifically 240.21, and then that's why we have 240.21B and we have C now. And this one
Right.
here is where we got connections from the secondary of the transformer. Now, this particular one, we're looking at C2, and this is connections um, uh, for 10 foot here. So when you go and you look at this, all you're going to do is like we've done before. All you're going to do is treat it just like we do a transformer calculation. You remember I did a presentation on here where I went through and just showed how to calculate transformers.
Yep.
This is the same thing for sizing your conductors. All you needed to know was the kVA of the transformer, multiply it by 1,000, put it in VA. Then you take the voltage. In this case, it's a 208 volt three phase, so I have to multiply the 208 volts times 1.732, which is going to give me 360, and I'm going to divide that into the kVA, or the VA of the transformer is going to give me 194.4 amps. Well, if I want to size the overcurrent device for that, I'll go over and look at table 240.6A for the standard ampere rating. The next size above that's 200 amp. And then if I look at table 310.16, 75 degree C column, come down 200 amps is for a 3-aught conductor. So in this case, I just sized it real quick, said I need a 200 amp overcurrent device and 3-aught copper conductors.
Yeah,
Okay.
and this is kind of interesting too. I kind of wanted to ask you this question. So if you were to have that on the exterior of the building, what was the limit? What would be the limit of the tap conductor?
There ain't no limit. And we'll get to
Yeah.
the outside transformer conductors here in a minute.
Okay.
And we'll show that
All right.
calculation. All
10
right. They're all the same calculation. Okay.
Right.
Like this one here, you're setting here, this is 25 foot. Okay. I do the same
Gotcha.
calculation. I've got a 200 kVA transformer. I'll multiply it by 1,000. It's a 208 volt secondary here with 3 phase. So I multiply it by 1.732. Do my calculation. The full load amperage is 555 point amps. The next size above that is a 600 amp overcurrent device. Now I'm going to parallel this one 3 times. Okay, we're telling you to do it 3 times. Well, a 3/0's good for 200 amps. So three 200 amp parallel conductors is going to give you 600 amps. And if you notice, did I change the calculation? No.
No, but you just
Calculation's
have to be
still the same.
careful because if you just all of a sudden at the end of your statement put in an adjustable circuit breaker, then you're gonna have to change your equipment ground. So.
Oh yeah, well, that's somebody that is trying to find a problem that was never a problem in the first place. Good job, Paul. You know, I heard that he took and was mouthing off about me again. Oh, hey, Paul, if one of you or your minions watch this, you need to go look. Maybe go look at the 70E committee, or you could go to the EECA committee, which covers NFPA 496, 497, 499. You'll see that I'm a member, and I have been part of the task groups that have done those. So to sit there and say I hadn't done any of this, once again, is nothing but a lie. Okay.
Sure.
And matter of fact, I was on there when they asked my dad to take and do to clean up the hazardous location portion. They asked him to be the chairman. Well, you know why they asked him? Because he actually knew what he was doing when it come to the hazardous location field. And then he had new members that were put on, and they helped clean that up. Well, guess who was in charge, Paul, of getting all the stuff together for the task groups that were put together to do that? Yeah, Dad had me do it. So, you know, when you come out and you're going to make all these false claims, you might want to get your facts straight instead of just mouthing off. And that seems to be what he does best at, is just mouth off about everybody. But
well,
anyway,
he says you never asked your dad, or your dad never set you straight on any of these what he calls misinterpretations, but he's all over the place because he says an outlet's any point on the wiring system, and that's not true. So,
well, you know, the way I look at that is, does he honestly think I don't ask my dad these questions?
Yeah.
I mean, give me a break.
Yeah, that's funny. I had a good time.
So here's one. You'll notice there's no length here we're talking about, and these are the outside feeder conductors. Okay, where I'm going outside transformer. We even put a new transformer in like you would see outside. We got a 750 kVA transformer, and you take and look at that secondary connection. What is it? It's 480 volt. It's 3-phase 1.732. That'll give you 831 volts. You divide that into the VA of your transformer, gives you 903 amps. Now, remember in this case, and we covered this earlier, 240.4B deals with overcurrent devices 800 amps or less. Once I get over 800 amps, then I'm looking at 240.21C. In this case, my conductors have to be equal to or more than the overcurrent protection device in this point of what the load is. Okay, so that means I have to be equal to it or drop down. Well, I had a 903 output. I can't exceed it, so I have to drop down to the next standard size, which is 900 amp. And then I'm going to look at what type of conductors I need here. And in this case, I'm going to need 350 KC mil conductors, which I'm going to parallel 3 times, which is going to give you 920 amps. Okay, I just know that off the top of my head because I've done it so many times. But what we like to point out here is make sure you know the sizing of your overcurrent devices and how you do it on the application of 240.4B and 240.4C. So Once you
Yeah.
see it's over 800 amps, you need to start looking at how high it's going up because you need to drop down at that point.
Yeah, and keep in mind, and we've had some guests on here. Big shout out to Reese, who we had as a guest on here. She had a little bit of a confusion when it comes to sizing the overcurrent device and sizing the conductors. So you have to keep in mind that when you're doing that, you have to keep the two separate, and you have to realize they're two separate things, and that's I think Reese had a little bit of a problem with that, but big shout out to Reese. I hope you you know pass your master, and
Sure.
that was
All right. Well, here's a busway. I'm going to tap from a busway. How hard is this? I said everything else you take at what? A third? So here's a busway tap. I've got a 150 amp busway and I'm going to reduce it in size. What is the minimum? Well, I'm going to take it at a third. That'll give me 50 amps. So I have to have at least a 50 amp busway there per tap.
yeah.
I could go up to 100 amp. But once I get to 150, guess what? It's no longer a tap at that point.
True.
Okay? I just want everybody to know what the difference is in taps.
Do you remember that one? Do you remember that question that I did, where
Oh,
I
yeah.
did the full size as the answer?
Oh, yeah. I remember it. Oh, looky here. Here's another one. Here's where we're doing a tap. We're going down to a motor here. Okay? It's 10 foot or less. What do I divide by? 10. If this was 25 foot, I'd take it at a third. So in this case, it was 10 foot or less. Divide by 10 gives you 80 amps. Now, if I go over and I look at table 310.16, I come down and pick up my 75 degree C column. The next size above that's 85 amps, which is a number 4 conductor. So therefore, the size conductors are required to be a number 4 copper. But if you notice, did I change anything that I've said up to this point about doing a tap?
No.
No. Kept it all the same. Did not do one thing different. Here's another one where I'm going over here and I'm doing the conductors from the generator terminals. Okay? I've got a 241 output. We're telling you that's what it is. How do I know that? Well, I've got a 200 kVA generator here, and I've got 480 volts. It's 3-phase, 1.732. Okay, and it'll give me 831 volts. Divide all that in, that gives me 241 amps. But now I also have to take that at 115%. So and people say, well, where do you get the 115%? Go over and look at 445.13. That's where you're going to get the information that I've got to put 115% on it. All we're doing is showing you in that illustration, how did I get that 241 amp output? Well, that's how I got it, by doing that calculation there. So take the 241 amps at 115%, it's going to give you 277 volts. And then I'm going to look at sizing this conductors. And the next size up above that is 300 kc mil conductors. Very simple. All of this is easy to follow. You just need to know where you're looking here. Okay. But the one thing I want to point out, when we were doing the secondary side of that transformer, the conductors for it, and then I'm doing it here for a generator, I still did the same calculation to determine what my full load amperage was. Okay.
Right.
Now, that got us through that. Now, what we're going to get into is looking at motors. Now, we're going to start this off a little bit different. All right. Everything I've done up to this point, I've based off of looking at 240.4B for overcurrent devices 800 amps or less and 240.4C. Okay. That was just how we went about the overcurrent protection devices, because sometimes we need to do that and to help us determine, make sure we're matching up with the size for calculating my conductor ampacities. This one here is going to be a little bit different, and this is going to be a prelude to what we're going to do in the next part, where we get into sizing overcurrent protection devices. So when you're looking at this, you would be looking over at 240.4G is where you're going to pick up your sizing for overcurrent devices, and these are going to be where you get over percentages that are over 125%. Okay,
Right.
so as we start to look at this, this is all going to tie in the same way. And the reason I bring up the overcurrent devices is because once I go to 240.4G, then I'm going to go look at 430.6A1, and you'll understand why I'm telling you this in just a second.
Yep.
When I look at 430.6A1, it says anytime, basically in a nutshell, this is what it's saying. Anytime I'm sizing my overcurrent devices and my conductors, I'll use one of the tables that's listed in tables 430.247 through 250. Okay?
Right.
So in this case, I've got, I'm going to size conductors here, and I have a 115 volt single phase, 3-phase design beam motor. Okay? Well, since it's single phase, everybody should get used to this. If it's single phase, you're looking at table 430.248, and if I'm doing 3-phase, I'm looking at table 430.250 to get my amperage ratings. So basically what I'm trying to tell you here is I'm going to use the amperage rating that's in the tables. Now, when I get over to AC units and refrigeration circuits, then you're going to use the nameplate. Okay?
Right.
And that's why we break this down, so you know where we're going to get these amperages. So in this case, for that 3/4 horsepower single phase 115 volt motor in table 430.248, it's going to tell you it's good for 13.8 amps. And then I go to step 2, and you go look at 430.22, and where I have a single motor there, you have to take it at 125%. Now, if I have multiple motors here, you take the largest motor at 125%, and all the rest of the motors are at it at 100%. Okay?
Nice.
Now, for this one, 13.8 amps times 125% gives me 17.25 amps. The next size above that for table 310.16 in the 75 degree C column is a number 14 conductor. Simple.
Ooh.
Okay?
Yeah.
And what's going to be interesting about, I don't know what it is, I have to do it in my head or pull out and add it, but you're going to see you're going to have a much larger overcurrent protection device. Okay?
It would probably be number 14 on a 30.
Yeah.
My guess.
I'm guessing that's what it is, but I have to do it, add it real quick. Now,
Yeah.
this is part of our new illustrations that I really like how these are done, because we actually show you the control unit. We show you the disconnecting means, how it would look inside, how you hook everything up. We show the wires coming in, everything's bonded in. I mean, it's fantastic. We even show the blue control wirings going down everything.
So right there, you're showing like 3 outlets, right? No, I'm just kidding.
Well, from what they're saying, you know, who was it? I guess Ryan. He said it was at the load side of the disconnecting means, and then I proved them wrong on that, and then they changed their stance on that and moved it, I think, to the equipment. And then I proved them wrong on that, and then they moved it to where it just connects.
Now it's just floating in the peckerhead now.
Yeah, it's just floating in an infinite space. Unbelievable. But anyway, as we look at this illustration, your known values, you got a 2 horsepower single phase 208 volt motor. You don't need to know anything else. All you need to know is go over table 430.248 at single phase, get your amperage, and then put 125% on it and size your conductors. Okay? So that's your homework next week on that. This one here is a 3-phase, the exact same thing. I've got a 208 volt 3-phase 15 horsepower design beam motor. Go over to table 430.250. 15 horsepower is going to require 46.25 amps. In step 2, we take it at what? 125%. That'll give me 57.75 amps. Go to table 310.16, 75 degree C column. The next size above that is 65 amps, which requires a number 6 conductor. Pretty simple. Okay. But the thing I like to point out, did I change the calculation at all? No.
Nope.
The only thing I did different was get a different value. That's it.
Yeah, and I like that. You guys will be able to follow that coming through this. Is nothing really changes. Like all they change is the theory and the calculation aspect of the values.
Sure. I had a guy that was taking his master's, and he struggled like 6 times before he passed the journeyman. I mean, he was really having a hard time. It was mainly calculations he was having problems on. And his dad was a contractor, and his dad called me. He goes, "I'm gonna hire you. I'm gonna have him drive to your house, and I want you to get him prepped for the masters because he wanted him to be able to take over the company one day." And I said, "Sure, come on over." And I was going through laying this out for him, and everything, and he went and took the test. Now he struggled on the journeyman, but when he took the masters, he made a 92. And the
Wow.
reason was because he understood the process. And he called me. He said, he goes, "Hey man," he goes, "I want to take you out." He goes, "Where do you want to go?" I said, "I was thinking about going and eating barbecue tonight." And so we went and had barbecue and had a beer and everything. And he said, "Man, I went in there," and he said, "I was nervous as could be." He goes, "But then I started he goes, the first question that was calculation. He said, "I knew it." He goes, "Then I got it." He goes, "I was thinking, God dang, man, this is easy." And I said, "It's really not that hard once you understand the process." And like this in here, you got 40 horsepower, 3-phase, 460-volt design beam motor. Where are you going to go? Table 430.250. Every time I'm sizing what? My conductor's an overcurrent device. I'm at one of those tables. And then I only have a single motor, so 430.22 says I have to take it at least at what? 125%. Then you do that, then you got your amperage, then you go to table 310.16, find the next amperage size above it in the 75-degree C column, and there's your size conductor. Now, here's one where you got multiple motors. Everything's still the same. I've got 460-volt 3-phase motors here, okay? I've got a 10 horsepower, 20 horsepower, and 30 horsepower. Well, I already know the 30 is going to be the largest. But I go to table 430.250, get all my amperages. So a 10 horsepower is good for 14 amps, 20 horsepower is 27 amps, 30 horsepower is 40 amps. Then I'm going to go down to step 2, and if I look at 430.24, the largest motor is taken at 125%, all the rest are added at 100%. So 40 amps times 125% is 50 amps, then add the 27 amp, the 14 amp motor, and that gives you 91 amps. Go to table 310.16. The next size above that in the 75-degree C column is 100 amps, which requires a number 3 conductor. Now, was that hard?
No, and it brings up one question that I want to ask though. So, like, are single motors always calculated at 125%? Is there any case where you could just take a single motor and calculate it at 100%? Like if it was like intermittent duty or something maybe, but I don't know. I just
Well, that's the only thing you would get into. You'd be looking at table 430.22E that gives you for periodic, intermittent, and those things there. That's the only place I know that you would get away with that. Matter of fact, we'll show that here in this presentation.
All right.
Okay.
Awesome.
And then when
I'm
you
sorry,
get here,
I'm not trying to predict the future on you.
don't worry. The great thing is we've been doing this for so long. I mean, between Dad and I, you've got over 80, almost 90 years experience, in the electrical trade. And all these illustrations and everything everybody sees, this is really pretty close to, I'd say, since we've been drawing, I'd say you're looking a little over 30 years that we have put a lot of technology into redoing all these illustrations and refining them. And, like I tell everybody, well, go look at the other publications. Like, if you look at this illustration, look at all them sections in there. All the things we're telling you you'd want to consider here. Even though it's not what we're doing, it's just extra information there. Okay?
Yeah, it's basically called a code loop.
Yeah. And
so
what I tell
you
everybody,
go back and double check and triple check and make sure you're on the right loop. And then as you're doing it, you're filling it out on the right hand side of the screen.
correct.
and you're double checking it with the code loop.
Mhm. And like I tell everybody, go look at other publications. You won't see this. And you know why? It takes a lot of time to go check all them sections. But it
Yeah.
just goes to show the amount of work and effort and time we put into this stuff. And like this in here, we show 3 motors. You got a 40, 50, and 60. All you have to do is get the largest motor, which is going to be 60 horsepower, take it 125%, add all the rest, 100%, get your total amperage, go to table 31016, 75 C column, find the conductor that's above it. It's that simple. Okay?
So is there any case where you would have to apply, um, like if you were under 100 amps, you would have to apply 11014C1 for that? Like
Well,
if the terminals were
you
unknown,
want
it
to
was
go to
under.
C1B, it gets into the motors, and that's where you got the 75 C. But you got to be careful, because if it's an older motor, it could be 60 C termination, and then you would
Gotcha.
be using the 60 C column.
Would
That,
there be anything if the terminals were unknown? Or is that just a general thing for motors?
well, if the terminals are unknown, it's based on the wire size going to it once you
Oh, gotcha.
make that determination. Okay.
Gotcha. Okay.
And that'll be spelled out in 110.14C1A and B. Okay.
Gotcha.
And this in here, this deals with phase conversion. Now, what you're going to see is a little variance here from what we usually see. But this is where you're protecting the phase conversion on the conductors and everything. And they're going to tell you that the conductors have to be protected. In this case, you're still going to look at table 430.250 to get my amperage rating for the motor. In this case, we have a 3-phase 20 horsepower motor. It's good for 54 amps. But if you go look at 455.682, it's going to tell you that it has to be taken at 250%, okay, for the conductors. Now, one of the things, well, I'm not going to do it now, but when we get into the overcurrent protection devices, anybody that's watching this, I want you to remember what I'm talking about here, okay? Because what's going to happen is the conductors, usually whenever you take and I have a rule of thumb where I say if you size an overcurrent device at 125% or less, you go up to the next standard size. Any percentage above that, you drop down unless it states otherwise. And I give you 2 instances when I give that rule of thumb. I said you really have to look at phase conversion because it tells you it has to protect the conductors. And in this case, they have them going up to 250%, which is 135 amps, which requires a 1-aught conductor in the 75 C column, which is good for 150 amps. But when I size the overcurrent device, instead of dropping down, I would put a 150 amp overcurrent device there, because in this section, it tells you have to protect the conductor. Okay?
Sure.
So, and the other one is when I get to transformers, and it has a note 1 in there, but it gives you the option to go up or down. Okay? Because it says shall be permitted. That's the only 2 places I'm aware of where you have to think about that. Okay? But when we get to overcurrent protection devices, y'all remember what I'm talking about here, that actually the conductor and overcurrent device are going to match up with each other. Okay?
So we have Raymond Quintero. Thanks for the like, sir. We have a motor that requires 230 volts, but we only have 208. Can the motor be connected? Ooh, excellent question.
Well, what he's getting into there, when you go over, and this was interesting because you'll remember this. Dad went over this a while back. Remember we had him come on. He was talking about the motors and everything. And one of the things that we got into, and he was explaining to everybody, was when you look at those motors, they're based on the frame of the motor and the voltages that are there. And that was one of the things he was getting into there. And he was talking about when you look at those, there's types that you're looking at. You got an induction type squirrel cage, and then you got round rotor. And when you come in and you you look at that, it gets in and talks about the torque characteristics and everything. Well, what they have when you get in, you start looking at that over in right on the side, it gets into talking about those different type of motors. And I'm going to do this off the top of my head, okay? Because I don't have the table right in front of me here. I don't have my code book out. I usually do all this off the top of my head. So when you get over there, it'll tell you right where it has the horsepower on the left-hand side. It gets in that talks about the falling values of full load currents, and it talks about what is typical for those motors running at those speeds, okay? And then it'll have the currents that are listed shall be permitted for system voltage ranges. This is where you want to look at this, okay? And what did he say? He had a 208 volt? Is that what he said?
No. So I've actually ran into this before as a 230 volt, and they only have a 208 three-phase. So it's a 230 volt motor, and to me personally, what I'm gonna say on this, Raymond, is the way I look at that is that's a nominal voltage. So as long as you have a nominal anywhere from 230 to 208, the only time I've had issues with that is when you have a demand, like a large demand, because what happens is that 208 volts drops to like 196,
That's
and
right.
that 208 volts drops below that manufacturer recommended voltage drop, and then that'll kill the motor. So you have to watch that. Like if you're not on a high demand for that motor, like if you're able to, like usually the way you do this, you run the motor, you run it under load, and if you watch the voltage stay pretty consistent, then you should be all right. At 208, it'll run fine. Usually 230 rating is just a nominal rating. So we usually run equipment anywhere from 230 down to 200. It's just fine. But you have to watch that. We've seen European equipment come out that was 230 volt rated, and the equipment was trying to eat 240 volt. You know, it was hungry for 240, and so you don't want to take that motor that's hungry for 240 and drop it down to 208. That's gonna damage the motor. But
Right.
in my experience, I've almost never seen a problem applying 208 to a 230 volt rated motor.
Yeah. Well, I can't even add to that. That pretty much summed it up. That's exactly how it works.
Yeah.
Matter of fact, we have in our generator transform motor compressor book, we actually have design notes in there where we talk about that. And then we go in and we also talk about the frame of the motor, because when you actually get into looking at the frame, that frame is set up for 220 to 240. Okay.
Right.
And, because a lot of people would say, well, it says 230 volts there, but I have a 220 volt, well, that's the frame. Okay. And that's why they have like a little thing over in the horsepower setting over explaining what that is. And you have a range between there. Okay.
True.
So, yeah, that's true. Okay. And then
thanks for the question. Thanks
for
the question, by the way, Raymond.
That's a good question. Here you got a 25 horsepower motor. You come in and go over to table 430.250. It's a three-phase, and then you're going to take it for 455.682 at what, 250%, and then you're going to size your conductor based on whatever your calculated amperage is. So everybody should be able to follow that just fine. Now, this one is where I'm getting in and I'm dealing with an AC unit, okay? And here I've got a compressor with a full load current of 38 or 33 amps, and then I've got a condenser that has a nameplate of 2 amps. Now, I want to point out, you notice here we're saying nameplate, Okay. The reason we're telling you it's the nameplate here is because when I'm calculating here and I look at Article 440, you're going to see that you are going to use the nameplate value, and I'm not going to go over and use the motor value that's given over in the tables. But the same principle happens here. You're going to take the largest at 125%, and all other motors are added at what? 100%. So looking at 440.32, you'll see we take the 33 amps at 125%, gives me 41.25 amps. Then I add the 2 amp condenser on there. That gives me 43.25 amps. Then I go to table 310.16, pick up the 75 degree C column. The next size above that's 50 amps, which is a number 8 conductor. Pretty simple. Okay. So just remember, the first set we did was the motors there. We use the table values. Now I'm getting in to this. Now, some will say, well, why would I do that? Let's address that right now. Because this is a listed appliance. Okay, in other words, it's a unit. It's an assembly. Okay, right. It's all been put together, and they know what's there. That's why you're using the nameplate amperage. Whereas I was doing individual motors, that's not part of an assembly where they put different motors in and created an assembly. In this case, an AC unit. Okay, right. Now, as I look at this AC unit, same thing. I got 19 amp compressor, and I got a 2.5 amp condenser. How do I do it? 19 amps is at 125%. The condenser is at 100%. Add all those amperages up. Then size your conductors based on table 310.16 and the 75 degree C column.
Welcome in. Justin Gibbs is in the house. Awesome. Thanks
Welcome,
for having
brother.
you.
Mr. Gibbs.
Oh man, he's got to go there. He's got to poke the bear. So
the answer would be no. We've been getting into that quite a bit here lately on a couple of things, and I submitted a proposal. I submitted many proposals, and I submitted them for one simple reason. I needed to establish in a location. It's hard to argue something when the location keeps moving all around the place. And now that I have a location, now I can submit in the second revision and show where they got a problem. So looking forward to that. All right.
Yeah, no, I appreciate it, Justin. Thanks for joining tonight. Appreciate you, sir.
Now, this one, like I said, you take the largest motor at 125%. Everything else is added at 100. Okay. So let's take a look here. I've got 3 compressors. They're all the same, 45 amp or 42 amps each, and each condenser is rated at 3 amps. So you'll see in 440.33, I took one of the 42 amps at 125%. Everything else was added at 100%. See that? So add all of that up, gives you 145.5 amps. Go to table 310.16, 75 degree C column. The next size above that's 150 amps, which requires a 1-aught conductor. Now, the thing I like to point out here, have I changed any of these calculations, really? The format, the layout, everything is exactly the same. The only thing you got to remember is how to do each one of them. But
you just got to be careful, like following James's, because you don't want to make the assumption you can just wire everything with a 1-aught.
Yeah, this was just to go in and just sort of show how all this worked. We do it like this. We did in single line diagram because it's otherwise we couldn't get everything on here. But we do show we got 3 AC units, and we're showing you all the AC units there. Okay. So basically what would I do out there? I'd go out there, put me a wireway, and then I'd tap off of that for each individual one. See what I'm saying?
And just to be a shout out to Justin in Colorado, none of them would be on GFCI protection. So
not in Texas either. And of course, by Jeremy's recollection of that, all of us here in Texas are nothing but glorified ditch diggers anyway.
Oh yeah, that was hardcore.
Yeah. I couldn't believe he said something like that. That's disrespectful.
Yeah.
I don't think he realizes how big our boots are down here.
Oh yeah.
Okay.
Oh, yeah.
So this one, what you look at AC unit 1, 2, and 3, the largest is the 40 amp. Then everything else is at 100%. Get all your total amperage and size your conductor going over there to tap off of that to feed each one of those. All right. Now, looking at this one, what size overcurrent device is required on the primary side to protect the conductors and panel board? In the example, we had an example we were showing here, but this is very simple. I'm doing here, showing a transformer here, and all I'm going to do is I had a 480 volt primary, 240 volt secondary with a 125 amp overcurrent device upstream. So we were just showing here how to do this calculation, and you do that. That gives you 250 amps. So I was going to size the conductors on that to protect the secondary conductors and the panel board that it was going down to. So if I had 250 amps, what's the next size above that? That's 255 amps in table 310.16 in the 75 degrees C column, which would have required a 250 kc mil conductor to supply that panel board. Okay?
225 is a standard size? Or 255?
No, that's for the conductor amperage.
Oh, gotcha. Okay, so it's on 250.
Yeah, and then we're showing you here where you go to a panel board and you're protecting the panel board.
Oh, gotcha. Okay.
And this just gives you something to look at here to, because sometimes they throw this on the test to protect the panel board. So you just need that primary and secondary, then get the amperage upstream. In this case, it's a 50 amp. By the time you do it, we actually gave you the answer in the illustration. It's 100 amp, but we wanted you to know how we determine that, and this is how you do the calculation. So it's just a quick calculation for everybody to understand how to put it together. All right. Now, this one is where we're going to size the copper conductors that supply the secondary side of a transformer that has a continuous load output of 181 amps. Now, if it is continuous, I have to take it at what? 125%. And that, in this case, I'm going over, it's a feeder, so I'm going to apply 215.2 A1A, and that's where I get the 125% at. So I take 181 amps at 125%, gives me 226 amps. Then I need a conductor for that. Well, I go over to table 310.16, pick up the 75 degrees C column. The next size above that's 230 amps, which is a 4-aught conductor. Okay? So as you can see, I'm just breaking down through this. Very, very simple. And the same thing here. I'm going to a panel board over here. I'm feeding it. Okay? I'm stepping down. All right? So how do I go about performing that calculation? All I need in this case is I need the kVA of the transformer, divide it by the voltage to get my amperage, and then I can start working on putting my percentages and everything in place.
Right.
Okay? And that's why I try to tell people, the way you go about doing these calculations is really not that hard. It's just knowing I've got to get the amperage for the transformer, okay? I've got to get the amperage for the generator. Every one of those calculations are exactly the same. The only difference is if I had a generator, I had to put 115% on it. In this case, I had a continuous load. I had to take it at what? 125%. Okay? So it depends on what you're looking at, but we try to cover every spectrum here so everybody knows where to find this information in order to perform this calculation correctly. Now, like this, and this is where I've got a capacitor, okay? I've got a 460 volt 3-phase 10 kVA capacitor, and it's going to serve a 460 volt 3-phase 50 horsepower motor, okay? And we're already giving you the information here. The motor is supplied by 480 volts, and it has number 4 THHN copper conductors, all right? So if I look at a number 4 conductor and I go over and pick up table 310.16, and come down to 75 degrees C column, it's going to tell you it's good for 85 amps. So I'm going to take that at a third. And you'll say, where'd I get the third at? Well, you're going to go look at 460.8A. That's going to tell you to take it at a third. And that's going to give me 28 amps. Okay.
Right.
Now, what you're going to do, we're actually going to end up doing two calculations here. Okay. The first one is where we're calculating the conductors at a third. And the second portion of this, we're going to be where we're calculating the full load current of the capacitor. All right. So in this case, I was at 28 amps. I go over to table 310.16. The next size above that's 30 amps, which is a number 10. Now, that's doing the conductors at a third. Now, also in 460.8A, I'm going to be looking at calculating the full load current of the capacitor. It's just like doing a transformer, generator, or anything else. I need to get the KVA of the capacitor, take it at 1,000, then divide it by the voltage. In this case, I have 480 volt times 1.732 for the three-phase, going to give me 831 volts divided into that 10,000, and that's going to give you 12 amps. But it tells you there that you also have to take it at 135%, which is going to give me 16 amps. Okay?
Right.
Now, as you go in the second part of it, number 16 is going to require number 14. But you have to use the largest between the two. Well, if I go back,
you're saying 16 amps.
16 amps requires a 14. But if I look at,
so you're going off the 75 degree C column, right?
Yeah.
Okay.
And then when you come here and you look, which was the largest between the two? Well, it's where I calculated the conductors at a third. Okay.
Gotcha.
So therefore, the answer for this particular one going over to that capacitor is going to require me to have number 10 copper conductors.
Okay.
Okay. And a lot of people
Gotcha.
never seen that calculation. You know?
That's a new one.
Yeah. And we go through all this. Like we did the illustration here. You'll see from where the controller is and everything, we have one of the new capacitor units in there. These are actually a digital type capacitor assembly, and it digitally reads everything. Okay.
Nice.
And this here is the same calculation. I've got 25 kVA capacitors, three-phase, 208 volts, and we're also telling you the conductors for the motor circuit are 3-aught. Okay. All you're going to do is the same calculation. You're going to do it based on calculating the conductors at a third and then calculating the full load current of the capacitor. And whichever is the largest between the two, that's the size, in this case, THHN copper conductors you're going to use. Okay? So I think that'd be really good one there because a lot of people don't deal with capacitors much. And then
100%.
The next thing we're going to get into is looking at non-motor generator arc welders, motor generator arc welders, and also resistance welders. Okay. Now, the first one we're going to do is a non-motor generator arc welder. There's actually two ways to do this. Okay. We're going to show you different methods, so you learn which one you like best and go from there. All right. Now, well, when I say two methods, it's when we're going to get into sizing the overcurrent protection device because you're going to look at two different things there also. All right. So this case, I've got a welder that's 68 amps and it has a 50% duty cycle. Now, when you get to looking at the duty cycle for a non-motor, you're going to look at table 630.11a. But in 630.11a, we already know that the welder is good for 68 amps. We gave you the information. Then I go look at the multiplier that's going to be based on the duty cycle in table 630.11a. It's going to tell you it's at 71%. Okay. And the 71% is based on it being a 50% duty cycle. Then all I'm going to do is just calculate the 68 amps times 0.71, and that's going to give you 48.28 amps. Go to table 310.16, 75 degrees C column. The next size above that's 50 amps, which requires a number 8 conductor. Okay. And then you come over here. Here you have a commercial type arc welder. We've redrawn these too. And you're going to see we have an 89 amp load and an 80% duty cycle. Step one, you got there, you got your welder, you know it's 89 amps. Then all you need to do is look at table 630.11a, pick up the 80% duty cycle, come across, get your multiplier, do your calculation, and size your conductors. Okay. And then when I get over here, this is a motor generator arc welder. Well, looky there, I'm doing the exact same type calculation. I've got 76 amps for the welder, and I've got a 90% duty cycle. I go look at table 630.11a, and it's going to now, I want to point this out. When I'm doing this for non-motor and motor generator arc welders, you're going to use table 630.11a. But when I get over and I start looking for the resistance type welders, you're going to look at 630.31a. We'll look at that in just a minute. So
and I think we had a good one come in, good comment come in that Danny mentions. You know, the NEC gives you a direction to adjust ampacity if it's more than 3 current conductors. So that's one thing you're going to have to really look at, you know.
Sure. And we actually did that in an earlier portion of this, probably about 3 or 4 episodes before. And I went through all that and explaining about the current carrying conductors and how to do the calculation for adjustment and correction factor, or a combination of the two.
Absolutely. That's a good catch, Danny, because that's something everyone has to remember is this is not just a be-all, end-all. You have to consider all these different temperature adjustments, everything. Like, you can't just assume anything in the NEC.
Sure. If they're asking you a question on the test, it would be like this. But if they threw in current carrying conductors and all of that, then you need to consider it. But most of the time, you'll get a question like this, and you just do it like this, and you're good to go.
It's all in part of dissecting the question. You have to make sure you dissect the question correctly.
Sure. I always, if I'm taking a test, I'm looking at plans or something. If I saw up, right here, there's 4 current carrying conductors. Guess what? I have a note there. That's something I need to consider after I do this calculation. It's in a temperature here. I need to consider this. All right. So we had a 96.96 multiplier. Take that times 76, give me 72.96. The next size above that's 85 amps in the 75-degree C column, which will be a number 4 conductor. Okay. And there you go. You got a motor generator. We got 65 amp load and 80% duty cycle. So step 1, 65 amps. Step 2, look at table 630.11, get the 80% there, come across, find out what the multiplier is, calculate it, and size your conductor. Okay?
Dude, have you been sneaking around my garage to get pictures of my welder or what?
I got some good pictures of everything.
Yeah, that's my welder.
Now, here you go. Here's a resistance welder. Remember I said when we get there, you want to look at table 630.31a. We got 91 amp welder with a 40% duty cycle. Same calculation. 91 amps for a welder. Look at table 630.31a for 40% duty cycle. Come across, it tells you that multiplier is 0.63. Multiply that by 91 amps. That gives me 57.33 amps. Then step 4, go to table 31016, pick up the 75-degree C column. The next size above that, 65 amps, which requires a number 6 conductor. Pretty simple. And here's my resistance welder we have. I'm telling you, boy, we have really upscaled these illustrations. Now,
it seems like you have all my equipment that's from my garage. That almost looks like my plasma cutter. I'm just like, where'd you get a picture of my plasma cutter from? You know?
I tell you, we've actually done a lot of research making sure we get a proper illustration. And I'll say this: these look good, but when we finish the hazardous location and that equipment, that's pretty incredible looking. But
I get the most amount of requests on my NAC code page for hazardous location questions and stuff. So I'm gonna try to fool James with the hazardous location next week. So we'll see.
Get after it. That's something I'm very. When I started learning code, my dad started me on calculations. And then he started me on grounding. He said, you learn these two real well. He goes, the rest of it comes easy. And then I got all that and I understood. And I mean, I've really put a lot of time and effort learning and asking questions. And then right after I got through that, he goes, now you're really going to learn. He goes, this is hazardous. And boy, and I spent about 5 years, I mean, really studying it. And I mean, I even got into going over, say, if I'm looking at NFPA 497 and you go over and look at the tables and you start dealing with your MIC ratios, your MSEGs. I mean, there's just so much in the table about the chemicals. I started learning about the chemicals. And then I even learned how to mix chemicals, put them in a group in order to help you determine locations and stuff. So,
yeah, I think that's funny that you're at dinner with Pops and he started talking about it. He's like, how'd you learn how to do that?
Oh, that was the one when I did that. He didn't know that one. And I was like, see there, you learn from us young bucks, you old fart. That actually happened. He was like, I didn't even know that one. I was like, oh, well, you know, there's a new sheriff in town now. You need to retire, old man.
I knew who to call.
Oh, man. But the reason I learned that, I was working with a chemical engineer that was helping me and teaching me that stuff. And he gave me books and everything. I started going in reading them. And when I got into that, I actually called him and I was asking questions. And it only took about 10 minutes before I understood exactly what they were talking about. And I was like, well, that ain't hard. He goes, yeah.
Well,
said, but a lot of people get confused.
Isn't it just based on the upper and lower level limits?
Not for that. Not for that. It gets into a little more than that because you got your maximum experimental safe gaps. You got your MIC ratio. I mean, there's more to it than just that. But the calculation is set up on percent of volume fill. And that's what you got to pay real close attention to. Right?
Okay. All right.
And then here we got 100 amp load, 40% duty cycle. So you should know automatically in step 1, it's 100 amps. Step 2, I'm looking at table 630.31A, picking up my 40% duty cycle. Get your multiplier, multiply those two together, and whatever your amperage is, you size your conductor based off of that. Okay?
Nice.
And then this one, what this is going to get into, we're basically proving something here more than we are anything. And this is over in 430.72B2. Okay? And this is where they're going to get in. And like this first one we're going to talk about here, this is where they're sizing some THHN copper conductors that are permitted in a controller where the upstream overcurrent device protecting the branch circuit is rated 90 amps. Okay? So when you go over, you look at table 430.72B, column B, it's going to tell you 90 amps permits for number 14. But how do I prove that? Okay? And if you look at the bottom of the table, it's going to tell you that it's based on table 310.17, and I'm going to use a 60-degree C column. So when you go over and look at table 310.17, you pick up the number 14 copper conductor. It's going to tell you it's good for 25 amps. But right below that table there, it's going to tell you in note 2, it's going to tell you take it at 400%. And if you take 400%, that gives you 100 amps. See that? Right. Which permits the number 14 conductor. Therefore, that 90 amp is permitted to protect those number 14 conducors. Watching from India.
Oh.
Wow.
Wow.
Man,
welcome in India.
Freaking going worldwide, baby. Bam.
Man, we're international. We're international.
Bam. Well, you know, Dad has done a lot of work overseas, and
dude, you even got a trophy in India, dude. See?
Well, you want to hear something funny? Is Dad was over in Saudi Arabia doing a class. He was actually on the base there, and after the class, they took their cups and started just sort of going back and forth with a handle and hitting the table like boom, 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 boom. And Dad was like, "What the hell?" He didn't know what they were doing, and the guy come up and he said, "They only do that to show sign of respect for the best, and they're telling you you're the best instructor they've ever had out here."
Nice.
And I was like, "Really?" I said, "Dang, man, they don't ask for much, do they?" You had to let Dad have it. So
yeah, that's funny.
But this one here's an 80 amp, and you're going to do the same thing. You're going to look at table 430.72B2 and then look at that note 2, and then you'll go get those amperages and then put that percentage on there to verify that table 430.72B works exactly as they say. Now, and I do want to point one other thing out. The reason they're using table 310.17 is because you're in an enclosure here. And when you're within the enclosure, that's considered free airspace.
Right.
Okay?
I agree. Dude, that was the first time. That was probably like 3 weeks ago. Oh, watching from Belize.
Damn.
Oh, dude, we were like hardcore international tonight, man. That's awesome.
Man, wow. Belize is nice. I've been to Belize. That's a beautiful place.
Yeah.
Wish I was there. Matter of fact, I like Belize.
That was total new information for me when you brought it up. That you actually go off a totally different table with a 31017 because you're in open air. So your ampacities, like even if you are, like some people consider it bundling, even if you are considered to be bundling, you're in open air because that's not inside the cable.
Sure,
so you're not bundling the cables.
The amperage changes.
Yeah. And I really enjoyed that. That was awesome.
Well, it was funny. I remember when they were having that argument, and I said, "Well, now y'all can't do that." I said, "You have to take a couple other things into consideration." When I brought that up, what's that song? The Sound of Silence.
Dude, I'll never forget when Weedman, I asked him the question like, "How can the utilization equipment be the outlet that feeds itself?" And he's a deer in the headlights, man. That was hilarious.
Well, sure it is.
That was so funny.
Now, this is where you're permitted to extend beyond the magnetic star. So that means it's not inside an enclosure. In other words, I'm running a conduit over to it. Okay?
Right.
It's some type of raceway. And you'll see it says upstream overcurrent device protected be 90 amps. Well, if you go over and you look, in this particular one, it's going to tell you in table 430.72B column C. So now I'm in column C instead of B. And it's going to tell you 90 amp allows a number 10. But look at this. Now I'm going over there. I'm not in free air open space going over there. So now I have to use table 310.16. And it's going to tell you in note 3 to apply 300% on it. Well, if I take and look at a number 10 copper conductor, it's good for 30 amps. I take that at 300%, gives me 90 amps, and it tells you, therefore, 90 amp could protect what? Number 10 conductors. So it's proven the point there. And I'm in high school.
Looks like you got a high school student that's learning from us tonight. So
yeah, well, that's what we're here for. You know, we provide it. Matter of fact, you know, people that are interested in electrical, go over to the YouTube channel. It'll be under Stallcup Electrical Education. That's STALL and then CUP, CUP. So Stallcup Electrical Education. That's the YouTube channel. And y'all go over and see all the videos. All we ask is you subscribe. It doesn't cost you anything, and hit the likes and all of that. Or smash those likes, Hulk like them. And
crush them.
You can go back and catch previous episodes, but we're trying to build that channel up. We've had it for years. We just never really pushed it. And just in the last month, we added, 100 and something? I don't even know how many we added.
So our goal is 1,000 likes by summer. We're a quarter of the way there. So, you know what I mean? Like, that's easy to do. You know, we could get like 250 tomorrow if we just keep pushing, you know. So
we don't really do it.
Yeah, you know, it just, just tell your uncle, your cousin, your brother, your like anybody in your family, like subscribe to our channel, and we're gonna hit 1,000 by summer, brother. We're
What
gonna
we're
see it.
trying. Now, if
Yeah.
you look at this illustration, see where I've got the control circuit conductors, but where are they going? They're going to a remote start and stop station. That's why you're not using table 31017, because you're got those control conductors going over there in a conduit. And that's why we're using table 31016. And then just do your exercise problem and put the 50 amps in there, and you know that once you go over and look at the table, it'll tell you what size conductor, and then you'll, based on that amperage, then you'll calculate it at 300%. Whereas if I was in the controller itself, I would do it at 400% because it's open air. Okay.
I'm gonna call this guy Raj. I'm gonna say, right on. Thanks, Raj. Appreciate you, Raj. So
Yeah.
yeah, we're gonna keep
All
going.
right. Now this one, you'll know this one because we actually get into this where we're dealing with motors in 430.72C4, and they're basically going to clarify exactly what you're allowed to do. All right. Now, when you come in, they're going to ask, could 14 AWGTH copper conductors be used on the secondary side of a control transformer that has a primary full load current of 1 amp? This is your transformer and control circuit conductors are inside control enclosure. The primary voltage is 480 volts and secondary voltage is 120 volts with transformers sized at 500 volt amps. Okay, so I'm going to take the 1 amp at 500%, and that's going to give me what? A 5 amp overcurrent device. Okay,
Right.
And then if I go look at column C in table 430.72B, it's going to tell me for a 45 amp motor branch circuit here that it could be connected to what? Number 14 conductors. So I'm going to prove this point now. All right. So step 3, I'm going to take the 408 volt primary and I'm going to divide it into the 120 volt secondary. So that's going to give me a 1-to-4 ratio. Okay. So when I get in and I'm looking at determine the proper protection of those secondary conductors, I've got a 5 amp primary times a 4-to-1 ratio here, and that's going to give me 20 amps on the secondary. So if I go over and I look at table 310.16 and tie it in with 240.4D for my small conductor rule, it's going to tell me that number 12 copper conductors would be required instead of the number 14.
So can I at this point call you a hack?
That
No,
ain't
I'm just kidding.
Uh-uh.
I'm just kidding.
But
you were trying to use 14 and you need 12, dude. Come on.
Well, that's why we show this, is because somebody would naturally assume it was a 14, but you got to look at that because the way that's calculated and everything, that might not be exactly correct.
True.
Okay. And then this one just gets into your control transformer. It's 1.5 amps. I'm not going to go through all this. I'm just work the problem and then we'll look at it next week. But I think that I'm almost done. Okay, I got just a couple more. This is just showing size and fixture wires here and how they can be used with a branch circuit that has number 14 conductors that are protected by a 15 amp overcurrent device, and we have a whip from the junction box to the luminaire. Now, that junction box right there, that you can call it junction box, but it's also an outlet right there. Okay?
Dude, you know what's so funny about that? Like, do you know why they permit you to use like number 18 gauge or number 20 gauge, whatever it is, on the fixture whip to the junction box?
Yeah, because it's already been listed and labeled in size for that size wire. They know how much amperage it's pulling.
Because it's technically a tap.
It's not really a tap.
It's a tap conductor, so it's.
I'd be careful calling that a tap conductor, because.
Well, I'm just saying that. Like, going from the outlet to the luminaire, it's, you know,
Well,
it's
you got to remember it. You have an outlet up there, and you're coming. You come from a whip, whatever. But when you get down to that fixture and everything, that to me that is, I don't. I wouldn't call it a tap, because if you're looking at tap, then you've got to go over and apply the rules in 240.21B, and there's nothing in there that deals with that. Those are really considered tap conductors.
well, so I've actually seen this before in the luminaires where they say you cannot take that 18 gauge, go to a fixture, then go from fixture to fixture to fixture because it has to tap directly to that junction box.
Now I agree
So,
with that. Uh, uh, well, yeah, because you got to look at that, because if you're going from fixture to fixture to fixture, and you're using that number 18, you put too many of them on there, then that wire size is not large enough.
true. Yep.
I mean, that would be where I would say that would be a problem.
I
Uh,
agree. I mean, I'm not necessarily calling it a tap, but the whole thing is it's technically how they size. I don't know personally the whole exact answer. I'm just saying from what I've seen, they're basically calling that a fixture tap to the branch circuit.
well, sure, and this. I understand the terminology, and that's why
Hmm.
when you look at this, you've got 240.5B2 to determine the protection, and it's not in 240.21, because they're telling you here that number 18 can be protected by a 15 amp overcurrent device. So they
Right.
have kept it separate from there just for that reason, because some people may have called it a tap before. And the
True.
reason they rewrote Article 240 is to get away from that. So when people say tap, I understand what you're coming from as a terminology, just like we
Right.
used to say just tap the secondary of a transformer. They had to
Yeah.
rewrite that so that wouldn't happen,
True.
because people would size it different.
Absolutely.
Okay. And then here's a good example. Like I was saying, you had the luminaire that's there, and you're coming over there with a whip. And this same thing here, we've got some known values. Got a 20 amp overcurrent device. You got number 12 conductors and number 18 conductors. Okay. Well, where are the number 18s? Those are where? That's going to be in the luminaire. Okay.
True.
So when they start looking at this and looking at the branch circuits, basically going to tell you that number 18 can go up to what? That 20 amp connect to it.
Yeah, and it's gonna be It's gonna be problematic for them to call the inside of that luminaire the outlet when the 18 gauge is actually terminating at the outlet.
Mm-hmm. Well, and see, here's a good one. Well, what if I'm inside a pole? Okay. I've got two number 16 copper fixture wires that run 60 foot inside the metal pole and terminated to two number 10 copper conductors protected by a 20 amp overcurrent device. Can I do that? Well, yes, you can do that, because if you go look at 240.5B22 and also tie that in with 410.30B, they're going to tell you those number 16s can be run that 60 foot and terminated to a number 10 conductor.
Right.
Okay. And, but I can see what you're saying. Some say I can tap here and go up and feed all this. Well, I look at it more as they're nothing more than fixture wires. Okay.
Right.
And then here's one here. You got number 16 fixture wires with a 55 foot length pole with 20 amp overcurrent devices. What size conductors are going over there? Well, looky here. We're making you think here, because I'm going all the way over here, and I had to upsize those conductors due to voltage drop, and I've got a number 8 conductor. Can I do this? You see what I'm saying? So you got to go look at 240.5B22 to make that determination. Okay.
Yeah, and you'd have to bond with the number 8
Right.
minimum conductor too.
We're almost done with this thing, believe it or not. That's
Okay.
why I was telling everybody, 12 weeks, I'll try, but by the time we go through it all, it's really going to be probably close to 4 months before we're done with all this. But they're going to ask you here, what size overcurrent protection device is required for a branch circuit with a continuous load of 20 1.5 amps with 75 degree C terminals. Well, all I'm going to do here, if it's continuous, I take it at 125%. So 21.5 amps times 125% is 26.8. We're just going to round it up to 27 amps. What is the next size above that for table 240.68? That's a 30 amp overcurrent protection device. Okay.
Right.
And then you get your illustration here. Same calculation. I've got 23.5 amps. It's continuous. I take it 125% and then size my overcurrent protection device for that.
Right.
I don't remember how many is even in this damn thing. All right. Here's
Well,
one.
dude, the complaint department is like going wild right now. I don't know. I mean, this is your complaints that you're getting right now.
I know.
They're putting trophies in there for your complaints. So I think we're good.
Okay. Well, we got a branch circuit, has a continuous load of 100 amps. What do you take it at? 125% gives me 125 amps. The next size above that's 130 amps. And table 310.16 come across. It's going to tell you it needs a number 1 conductor. I'm going to protect the conductor in this case, which is going to be a 150 amp overcurrent protection device. Now, let's look at this a little bit further. Could I put 100? We'll just leave that. We'll just leave it at 150 amps. Okay. Here it is. I've got 90 amps. It's continuous. What I take it at 125%. Then you size your overcurrent protection device and conductors based on whatever the calculated amperage is. That's for your homework. And that gets us through all of the calculating conductor ampacities. And we'll do the homework next week. And then we're going to start on sizing overcurrent protection devices.
Awesome presentation, sir. Appreciate it. Everyone in here is loving it. And everyone out there worldwide know James Stallcup is the #1 best educator in the world right now. So that's pretty awesome. I appreciate you. I appreciate you bringing the heat.
You need to rephrase that. The universe.
Yeah. All he has to do, the only thing he has to do is beat me in 1 round of pool. So that's still yet to be proven.
Oh, that's going to happen one day. We're going to do that.
Yeah, he thinks he can beat me, but I don't know. We're going to have to see because I kind of have a little bit of some skills on some.
He's faking that ass.
Some 8-ball. But it's going to be BCA rules, and I'm going to make sure that I cover all my bases on that.
He knows I win one game. He's never going to hear the end of it.
Wow, yeah. Jose up in the house. Thanks for joining, Jose.
Hey,
First time jumping in here. Yeah, awesome. Jose, stay tuned. I have an easy quiz coming up, and James is going to smash it out of the park. Everyone is welcome to join in on the quiz. And we have it like, are you going to beat James in the quiz? I can guarantee Daniel J is going to swoop out of a tree tonight, and it's going to be epic, you know?
All right.
Yeah, thanks a lot. Appreciate it. Thanks, Danny. Thanks for joining. We really appreciate it for joining. It means a lot. We do this for free and just jump in and subscribe to the channel. Oh, Daniel's in the house. He jumped in.
Yeah, no, man.
Yeah, so he thinks I'm giving you the answers now. He's gonna Daniel's gonna make a podcast about how you get all the answers and it's all rigged and everything. So all right.
It's only
Daniel,
rigged if I get them right. But when I go 0 for 3.
I have a funny surprise for you tonight, so you're gonna love it. I did a little.
Apple. I know. I use Apple products. I'm in, baby. That's my.
All right.
I dig on that. All right, let's do tool of the week. I want to get into it.
All right, let's do it.
It's time for tool review of the week. Sponsored by Electrician's Only Tool Review and Nipex Tradesman.
Alright, thanks a lot everyone for joining every week. Tool Review. This is a freaking awesome new product. I'm not sure if it's actually hit market yet. I know it's close. I think it's probably going to be released in the next couple months or like weeks or whenever. It's really close, but it's the first ever mini DeWalt bandsaw that can cut 3-inch. I like the design of it. I've been following this for a minute. I'm not sure exactly. It could be out now because sometimes I see like these new products and they're like coming soon, but it's already out. I don't know if it's already out or not, but it takes the regular DeWalt battery. It takes a regular 20 amp or a 20 volt. Just takes a regular 20 volt. It's not the flex volt. So it has plenty of power. I really like the design, what they did with the little catch thing underneath. I really like that. It's a really cool design. They did it with their mini. There's actually a mini that we did a review on. I really like a lot of the stuff about it. And I can't even think of a downside of this. I really want to look at what blade it takes, because if it takes the 32 7/8, the same as the other mini, the same one I have the other mini that doesn't have, like my mini can cut up to 2-inch. This one I guess can cut up to 3-inch. I'm thinking maybe even 3.5. It says the opening right there is like 3 7/8 or 3 5/8 or something like that. So I'm not sure, but it's the first DeWalt mini deep cut bandsaw. So I think this is going to be a good one. And no, Daniel, it is actually 20 volt. So it's a 20 volt. It's a 20 volt DeWalt. So that's my review. And I recommend Daniel go buy one the minute it comes out, because, that's going to be awesome. And I really hope, I really wish Daniel luck in this week's Willie Quiz. I think he could get James this week because it's so easy. It's the easiest quiz I've ever done. So,
All right, let's get your question of the week out of the way. Let's see what you got for me. Okay, where a feeder tap is made, how big is it?
I don't know if you're familiar with Joe's Mobile Home Factory, but it's a very profitable industrial factory that I actually was employed with. I do consulting with Joe's Mobile Home Factory. They're the leader in mobile home productions, and
okay, so
we have a union side, a non-union side.
It's a joke group or something. I can see what you're doing.
Yeah.
Okay, so this is in 240.21B4 we just looked at, and I know what you're asking. There's some other things you got to look at in this, as I was showing in the illustration, but the answer is B, 30 foot. I know what you're going for.
Yeah, you actually had the answer in there, and I was doing the Michael Scott, like, just giving that face, like, oh man, he's got the answer right in it. Like, even in your illustration, you had the answer. I was like, ah, dang it. But
I'm not missing that one.
I know, I was like, ah, man. But it's all good. I wish Daniel all kinds of luck tonight, because we're getting ready to roll the Willie Quiz.
Here we go.
You are now entering the zone of the Willie Quiz. Enter at your own risk.
All right. So if you guys are first time joining, you will enjoy this Willie Quiz. So what I do is I try to just take random facts, random topics, and I try to, let everyone join in and answer. So put your answer in the chat, and I will recognize you. James wanted me to do apple again, and I did, but I didn't tell you. I was doing apple to fruit this week. So,
that's shit.
yeah, so I wanted you to study and everything, but this is a good one. This is a good one. I think everyone's gonna like it. So, question number 1: apples float in water because blank percentage of their volume is air. A, 20%, B, 25%, C, 30%, D, 35%, or E, they just float randomly. Good luck, everyone. Oh, Daniel comes out of the gate right for the throat. He goes 25%. Boom! Daniel has an instant answer. He's coming for the throat on Stallcup tonight.
I have no freaking clue.
Oh, dude, Daniel's freaking on it.
I'm just gonna go with Daniel on this. I'm gonna go with B. I had no freaking clue.
All right. Stallcup is gonna copy Daniel.
I am. I'll admit it.
So you guys decided to go with a really good answer. That's like a really good answer, and you're both correct. So B is the answer. Is 25% of the volume is air of an apple. That's why they are great for apple bombs. But
I had no
I knew you. I think it's awesome because Daniel gets one, you get one. So now the heat's on for question number 2.
That's funny because I didn't even have a second answer.
Yeah.
Okay,
well,
let's see what 2 is.
Hopefully you have a second answer now.
Actually, I know this one, I think. Okay, go ahead.
It takes about blank amount of apples to create 1 gallon of apple cider. Is it A, 22, B, 32, C, 36, D, 41, or E, a random number depending on the batch or apple or whatever it is? Good luck, everyone. All right, so I went and I called Daniel ahead of time and told him what all the answers are, and Daniel's saying C, 36. So I don't know. We'll see.
This is interesting because I remember, God, you stumped me a little bit there because my aunt used to make homemade fresh apple cider.
Right.
We had it every year, and just passed away, my Aunt Rebecca. And she made it at Thanksgiving. And she also did it at Christmas Eve. And I remember her doing it. She said it took around 30, 40 apples. So it's not a specific number. It depends on how many apples. So if that's the case, there's no set number. So I'm going to go with E. It depends on how big the apples are, how juicy they are. I mean, they're always different. So I'm going to go with the E.
So that's a really good answer, E. All right, so I really hate to do this to you, James, but they did a lot of research on it, and they figured out that Daniel was correct that it is almost exactly every time pretty close to 36. Like, it might be a little bit over 36, it might be a little less than 36, but it's almost always 36. And it's funny because they actually based that on it takes 3 bushels.
And that's what I was saying. That's why it's like 30 to 40, and it.
Yeah, and 3 bushels is almost. It was. I did a lot of research because I wanted to make sure you didn't have the instant replay on me, but it was almost exactly 36. Like almost every time. You know what I mean? Like it was. It might have been like 38. Might have been like 35, might have been like 32, whatever, Like, it wasn't 32. It was like, it was within that range. That's why I checked my answer to make sure that. But you are technically correct that it's a random number depending on the batch. But that's not the right answer. So.
God, dude. Well.
It's all good. I just wanted to make sure that you and Daniel are going to go neck and neck for question number 3.
All right.
So everyone knows that apple pie is known as being American, but which continent does it actually originate from? Is it A, Asia? Is it B, Africa? Is it C, South America? Is it D, Europe? Or is it E, Antarctica? Good luck, everyone.
Okay, before you put Daniel's up, I'm pretty sure I know the answer to this. And I remember this. I think I saw it, that it was on Food Network, and they were talking about they were doing different pies and stuff, and they were talking about certain fruits come from different places and all of that, where it got started. And if I'm not mistaken, that they said apples originated for doing this in Asia. So I'm going to go with A.
Okay. So Stallcup goes with A, and that is a real good answer. But actually, Daniel is correct with the answer of D. It is Europe. It came apple pie. So you are correct, James. I knew I was going to get you on this because you are correct. Apples originated in Asia, but Europe was the first place to put it in a pie format and then send it to America with our immigrants. But awesome. Yeah. Daniel J's third win, Daniel. Like, dude, I'm going off like Super Bowl parade for Daniel. But that's so awesome. I can't believe Daniel beat you 3rd time in a row. Like, dude, Daniel's
2 answers I knew where it came from, and I had a legitimate answer based on things that I thought, and I still freaking wrong. God.
No, you were right. Like, that's why I put that answer in there, and that just is a shout out to all the people that are getting ready to take like their license out there. They put the wrong answers on the test for a reason, so that if you get that you do that calculation, you get that wrong answer, you think it's right, you have to double check it. You know what I mean? So
Son of a bitch, I thought I
James
had that.
did not double check against Daniel's doing the discount double check. You know.
And that is just amazing. I know this much about, but I store all these little pieces of information, that something I'm watching them like, oh, I didn't know that. I just remember that. And tag it on, give me a break. I said, oh, that's just not fair, Daniel.
Dude, I'm telling you, Daniel, the podcast coming out against you it's dude. When you see it, I'll tag you, Daniel. When James produces the Daniel J is a cheater in the Willie Quiz. When he puts out the podcast, I'll tag you. I'll send it to you so you know. Because
I'm going to go back and I'm going to do, since we started this, and I'm going to show how many I've missed. Everybody be like, I'm probably below 50%. I'm right at it. I'm 50-60% getting them right.
Right.
So I should, if I knew even remotely the answers, I should be up 70-80%. Yeah. And I'm barely hovering above 50%.
The thing is, like, it's so much fun for me because
I love it.
Like the reason I tried to start doing it was, remember when I got you on the Super Bowl?
Oh,
I got you on the Super Bowl last year. And we were just doing a Super Bowl thing for fun. And I asked him all these Dallas Cowboy questions for the Super Bowl.
And I got the second answer every time.
Yeah.
I was like, God. I said, it's one of these two. But I just couldn't remember the exact, and I missed it, but I knew it was one of those two.
But I knew you were, oh, wow, look at... Oh yeah, we have to get Weedman on. He's a union guy. Daniel loves having the union guys on here. Like, dude, me and Daniel have this joke where we say just another perfect non-union install,
Mm-hmm.
And it's so funny because we post it out there, and next thing you know, like they don't know what to do because they don't know, like, are you union and just trolling them, or are you non-union? Like, they don't know. Like, on social media, it's fun. Daniel sees it. It's a lot of fun.
Amen to that.
So what we would do, me and Daniel saw this. I was like, so we'd get these prefab buildings that would show up, and we don't even know where these are from. Where they're built at or anything. They're probably built in, like, Mexico.
Mm-hmm.
And they have all this, like, pipe work that's ran in them. That's already done. It's all surface mount and everything. And they just crank these things out. So then I was like, watch this, Daniel. I was like, I'm going to just take a picture of this pipe work and I'm going to post it and be like, I just taught my first year apprentice how to bend pipe,
Mm-hmm.
And dude, Daniel was not disappointed at all. I mean, I think I got like 400 comments or something. These people were like, oh, your apprentice sucks. Why do you use minis? But a lot of times, like, out in the gas and oil, when you're going from, like, enclosure to enclosure, they want you to use minis. They don't want you to use box offsets, because what they want to do is they want to be able to clean behind it,
Right.
If you get, like, the oil or whatever, like, gets sprayed all over everything, they want to be able to clean behind the conduit,
Mm-hmm.
And so they put it out as like a spec. And so I just told him, I was like, watch this. I was like, watch all the different things. Oh, he was not disappointed. He's like, what? He's like, you got 400 comments on that? It was just this prefab building showed up. I was like, yeah, just taught my first year how to bend conduit. He's like, what? He's like, how did you get that many get that many comments? And it was just funny. He's like, oh man, you're just like triggering people, huh? I was like, maybe.
It depends.
Yeah, it was just fun. But I think everyone will really enjoy the what is it? Wall of Shame this week.
Wall of shame. Here we go.
Shame. 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 Shame.
All right. Let's see what you got this week.
Oh, dude, it's freaking Stanford. He twisted the ground wire the wrong direction and torque marked it. So,
Really?
yeah, I don't. It triggered a lot of people, but is it a code violation? I don't see nothing wrong with it.
Look at it there.
So the ground is twisted the wrong direction. So what you're supposed to do is you're supposed to twist your wire around your conductor around the same direction.
Yeah, I know what you're talking about. I'm just sort of looks like it's in there pretty well.
Yeah,
I mean,
I don't see nothing wrong with it.
I don't think anybody'd even deny that. I don't know.
He was trying to trigger people for the screw direction. So you wrap the conductor the same direction you wrap the screw. But I don't think there's
nothing in code that says you can't do that. I mean,
yeah.
I understand what they're saying, but I mean, it looks like it's in there pretty well.
He is correct with the torquing because there is a torque on that screw, but you know, you don't have to mark it or anything. You can if you want.
I was just looking at it. I didn't see anything like severely wrong with it or anything, but I can see what people gripe about anything.
Dude, he said he's a 24-month apprentice, and I was like, I could vouch for 12 months of that. Anything else is out of warranty.
All right. Well, dude,
I appreciate.
It's already over 2 hours.
Yeah, I appreciate everyone joining. I appreciate Daniel. Dude, we are gonna ask Weedman if he could come in and be a moderator. We'll be like, hey, me and James are gonna get an argument, and you need to come in and moderate us.
He couldn't handle that.
That'd be so hilarious.
All right.
You're like, all right, you're gonna be the moderator. We're gonna be debating.
Love it.
I'm gonna tell you it's an outlet. You're gonna tell me it's not. He's gonna moderate.
He's hell about anything, I swear. All right, let's wrap it up. I'm tired. I'm gonna go eat. I'm hungry and cranky.
I just want to tell everyone, remember, make every day an easy day.
That's right. Everybody remember to do your homework this week. That'll finish up calculating conductor ampacities. Next week, we're going to start the overcurrent protection devices. So,
thanks for all the likes and thanks for all the subscribes.
Amen.
And we'll see you next week.
And everybody that showed up from overseas, too. We appreciate that also. Y'all keep coming back. So, look, some kind of kung fu fight. Everyone was kung fu fighting. Da, 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 da. All right, let's wrap it up. Everybody have a good one. We'll talk to y'all later.